Greetings to all of you, and you are welcome to today's lecture. And today we will continue with our design. Today we have our lecture 4, still on design of beams, but we'll be focusing on doubly reinforced beams. Right. So as usual, we'll be dealing with bending only, as I have already indicated. Shear and deflection will be considered separately for better understanding. At the end of this lesson, you should be able to differentiate between singly and doubly reinforced sections. You should be able to explain when doubly reinforced section is required. Understand code provision for design of doubly reinforced beams. Derive formula for calculating area of tension and compression reinforcement. And also design doubly reinforced rectangular beam section for bending. Right. And this is the lecture outline. Now, in our previous lecture, that was lecture 3, we learned more about code provision for design of beams in accordance with BS 8110 and other relevant codes. And we learned how to design a singly reinforced beam section. Now, what we discussed, the beam itself has its own capacity, which essentially we are talking about the concrete capacity. So if in a case where the moment capacity of the section, if it is bigger than the moment due to loading, in other words, the design load, then we will be able to say the section is singly reinforced. In other words, the concrete in the compression zone will be able to do all the work in the compression zone. As you already know, in the tension zone, the concrete strength is ignored. And so if the beam would have to be reinforced only in the tension zone, and then the concrete will work in the compression zone, such sections are referred to as singly reinforced sections. Now, so either you compare the design moment with the ultimate moment capacity, or you compare the K factors. As you already know, there are instances where, though we know concrete is strong in compression, there are instances where the concrete in compression cannot do the work alone. And so if the bend moment is bigger than the moment capacity of the concrete in compression, then it means we need to add some steel to be able to work together with the concrete in the compression zone. And so in such members, we will provide reinforcing steel both in the tension zone and also in compression zone. And if we have a case of that nature, we call it doubly reinforced. Now, basically, if you have a beam, right? If you have a beam like this, okay? So let's say this is 500. Let's say this is 250. If this beam, the concrete capacity is less than the moment capacity, one other means of ensuring you get a singly reinforced beam is to try to increase the depth of the beam, right? By increasing the depth, you would be able to meet the requirement of singly reinforced. Again, but let us not forget that when we have a floor or when we have a building, we have the floor to floor height. So let's say if this is ground floor and this is first floor, there's floor to floor height. Now, so let's say it's 3.15. This height usually is limited. So in a case where if your beam drops too much, it's going to create problem for the users of the structure. Then it means that you don't have the luxury of continue to increase your depth because you want to meet, you want the beam to be designed as singly reinforced. So because of depth, story height restriction and all that, there are instances where we would just have to provide reinforcement in the compression zone rather than increasing the depth of the beam to ensure we have a singly reinforced section. Now, so as you can see, this particular section is a singly reinforced section. Basically, the rows here, we call it hanger bars. They are not compression bars because the concrete alone in the compression zone can do the work. So what usually happens is because of the links, we need something to hold it. That's why sometimes they will even just provide one and use triangular links because we don't need any steel in the compression zone. But the other one here, this is the what do you call it? Doubly reinforced. There's tension steel and compression steel, right? So in the compression zone, both the concrete and the steel is resisting the bending, whilst in the tension zone, as you already know, only the steel is considered because the concrete would have cracked. Concrete in tension is very weak, as you know. So once the concrete cracks, it's of no use, and so in the tension zone, concrete is completely ignored in terms of bending, right? So that's essentially what it means to have a singly reinforced and doubly reinforced. Now, we want to look further into the derivation of equations for bending in terms of the doubly reinforced sections. Now, I want to take a bit of time to explain this diagram. So I would want all of you to pay much attention and then get clear understanding of even the nomenclature and all that. So this is the beam section, as you see here, right? So if you have a beam section, the overall height of the beam is what is called H. Good. Now, the depth from the, you see, the top is in compression and the bottom is in tension. So let's note that the top is in compression. So the depth from the compression face all the way to the centroid of the tension steel, right? That depth from here to here is the D, effective depth. So effective depth is the depth of the section from the compression face all the way to the centroid of the tension steel. Now the AS represents area of tension steel and the AS prime represents area of compression steel. These are nomenclatures we'll continue to use, so it's important to understand them. And we have also what we call D prime. What is D prime? D prime is the distance from the compression face to the centroid of the compression steel. You get it? Distance from the compression face to the centroid of the compression steel. So if you want to really calculate D prime, you know that we have cover and then you have diameter of your link and then diameter, you also add half the diameter of your compression steel. You get it? So D prime is called depth to compression reinforcement. Now the NA here is the neutral axis. Is that okay? Now if I draw a line through the tension steel, it's going to be like this, right? So this FST is the force in steel, in other force in tension steel, right? Okay. And then if I draw a line through this compression steel, you see that it's going to pass here like this. Okay. It should be able to pass through this one. So you see this one, okay, is FSC, force in steel in compression, and then the FCC is force in concrete in compression. And this one is very simple. Now, as you know, the depth from the compression phase to the neutral axis is what? The X. Is that right? And the X is taken as half of the effective depth. So X is equal to D over 2. Now, you see, this is the section, this is the strain diagram. So the strain here, this is the epsilon ST, the strain is still in tension. And then the epsilon SC, the strain is still in compression, which is this one. And then the top here is the failure strain in concrete. Okay, this one is epsilon CC. All right. Now, we learned about simplified stress block, and we said instead of the parabolic stress block, it has been converted into a simple rectangle. And that one, the height of the simplified stress block is the S, which is equal to 0.9x, right? So once the force in steel in compression passes through the compressive steel, the centroid, and that for FST passes through the force, the compressive force, the tensile force in the steel in tension. If I have this one, the S here, okay, which is the depth to the neutral axis, to be somewhere here. So all the concrete above this line is considered as the concrete in compression. Is that okay? So if this one is S and the width here is B, then the area is equal to what? The S times what? B, isn't it? We know the S is what? 0.9x. So it's the same as 0.9x times B. Right. Again, in this same diagram, this is the stress block, right? And remember that the force in the concrete passes through the middle of the concrete in compression. So the middle of that concrete in compression will be half of the S, right? So from here all the way to here is what? S over 2. And the remaining one would also be S over 2. Now, this is the stress block. So the stress here, okay, is the design stress, concrete stress, which is 0.67 FCU over what? Gamma M. And we know gamma M is equal to 1.5, right? So when we put in this, we'll get it approximately 0.45 FCU. Is that okay? Good. Now, for example, if we want to find equilibrium of forces, you see the FST is moving to the left. So that should balance, in order if I sum, I should get 0. it should balance the FCC plus the FST because these two here are in the same direction, whilst the force in the steel is in the opposite direction. So for equilibrium, the total force should be able to give us this. Okay? Right. So as you already know, the distance between the force in concrete in compression and then the tensile force is the Z. Is that okay? Which is called the lever arm. Now, let us remember that if this, okay, the distance between the steel in tension and the steel in tension and the steel in compression is from here all the way to here. And that's very simple. From here to the top is D prime. So this one, if I take the overall D and subtract D prime from it, I'll get this distance. Is that okay? All right. So I think that this is clear enough. This has been done so that you get a clear understanding of the doubly reinforced section. Now, with this that I've explained, we will use it for a few things, okay? All right, so let's proceed. So whatever I've explained, all the nomenclature also have been defined here, okay, so that you can be able to relate very well. Now, so looking at the compression zone, I think I have explained what is force FST plus, they have explained this, right? Now for reinforcement at yield, okay, this is the force in tension steel, okay, and design strength for steel is equal to the Fy over what? Gamma M. And we know for steel, gamma M is equal to 1.05. So if I divide 1 over 1.05 times the Fy, I'll get approximately 0.95 Fy. Okay? And this is because we are converting all the, we are writing them in terms of force. So we know stress is what? Force over area. And so force is equal to stress times area. And that is what we are having here. So times the area of tension steel. And if you look at the concrete, I've already explained that the stress in the concrete is this one. Okay? And the area of the stress block, if you remember, is the BS, as I already explained. And then the force in concrete, still in compression, is the same force, except that the area now will be the area of compression still. So this ABCD, substituting into equation 1, will give us the equation 2. And remember, the depth of the stress block is what? 0.9x, right? Which will give us 0.45 D. Good. Now, so when we do that substitution, okay, because from here you see that our S is 0.45 D. If we substitute the value of the S into the equation 2, we'll get what we have here. Okay? We'll get what we have here. Okay? So if you multiply 0.447, 0.447 is the 0.67 over times FCU over gamma M. Okay? When we approximate to 2 decimal places, 0.45, but into 3 decimal places, 0.447, right? Now, when you multiply that by 0.45, you get 0.201. Okay, and we'll get equation 4. Now, taking moment about the centroid of the steel. So this is a simplified stress block. Is that okay? This one is the FST. And we have one here as the FCC. And then we have one here as the FSC. And the distance between this one and this, okay, is the Z. And as I explained, the distance between this one all the way to here is the D minus D prime, as I explained in the previous slide. So if we take moment about this point, then is this force times the distance and this force times. So that's what you are seeing here. Okay. Now, so the force in concrete has been re-expressed here. Instead of 0.45, we are using this one for more accuracy. And that will give us 0.201 FCUBD. And then the force in steel in compression is also here. And as you know, the Z, okay, the Z, as you know, from here to here is what? Is the S over 2. So Z can also be equal to what? D minus S over 2. That's what you are seeing here. And simplifying that to get 0.775 D. So by substitution, we now substitute what we have done into the equation 5, and then further simplification. So this one by this will get 0.156, and then we'll generate the equation 6. Okay, good. So from the equation 6, okay, from this equation 6 here, if we make AS prime the subject, we would get equation 7. Okay? We'll get equation 7, making AS prime the subject. And let's recall that K is M over SCUBD squared. So we can find a substitution for M, which is K FCUBD squared. And we also know that K prime is 0.156. So instead of 0.156 here, we'll put K prime, okay? And instead of the M here, we will put KFCUBD squared, okay? And then doing that, we will now simplify the equation to be like this. So we have K here, K. This one should have been K prime, okay? So we can now factor FCUBD squared out, and when we factor it out, we would now get AS prime to be K minus K prime FCUBD squared all over 0.95 FYD minus D prime. So this equation 8 is very important equation that is used to calculate area of the compression steel. So this is the first equation, and this equation can be found in clause 3.4.4.4 of the BS 8110 part 1. Let's proceed. Now, let's recall equation 4. And from this equation 4, if we multiply both sides by Z, okay, it will simplify to equation 9, right? And from the equation 9, if we can make AS the subject, and we'll get equation 10, okay? We'll get equation 10. And let's recall again that in this equation, this 0.156 is actually a K prime. Is that okay? Good. So in substituting K prime into this equation, we have now got formula for calculating area of tension steel, right? So this is the formula for calculating area of tension steel. And the Z is calculated from the same Z. But I want to emphasize the main difference between the Z formula for the doubly reinforced is that the K here is rather K prime, not K. So for doubly reinforced, the K is K prime. So ensure that you don't use the K to do your calculation if you are designing doubly reinforced. Otherwise, once your Z is off track, every other thing you do will be off track. So remember that for doubly reinforced, the K here is K prime. That's the main difference between the lever arm formula. Okay? All right. So for doubly reinforced section, the area of compression and tension steel is calculated using equation 8 and 10 if d prime over x is less or equal to 0.37. So the force in the compression reinforcement is dependent on the stress and consequently the strain. So in order to ensure that this is greater than or equal to the yield stress, the ratio of d prime over x is limited to 0.37, which is also in the code. Now let's progress. Now let's learn something small from here. This is the same strain diagram, but we are just considering the compression zone. Okay? From this particular, this similar triangle. So, okay? So this particular one over this is equal to this over that. Okay? The rule of similar triangle, then you get the equation 1. So from the equation 1, if I need d prime over x, I can make d prime over x the subject, and I'll get this particular equation. Is that right? So for FY460, the yield strain is 0.002. So if I decide to put this value as 0.002, okay, that will yield in a value of 0.43. So d prime over x must not be greater than 0.43. So to ensure the compression reinforcement yield, in order to have a ductile failure, in order to have an under reinforced section, which I told you, the code makes certain provisions to ensure that the section that you design fall in the category of the under reinforced section. Is that okay? So when you check this factor, the code is saying it should not exceed this. Okay? So once you're obeying what the code is saying, particularly about the Z and the X, the depth of the neutral axis or depth to neutral axis, your design will fall within the under reinforced section, which we said that gives a ductile failure. But the over reinforced will not even give you any warning. It's very brittle kind of section. Good. So therefore, to ensure yielding of the compression steel, the d prime over x must not exceed 0.37. Okay. So, for example, the neutral axis, okay, is limited to d over 2. So if you have d prime and the neutral axis is x, we can put d over 2 here. Okay. And we say it should not exceed 0.37. So d prime over d, okay, can simply be should not exceed 0.37 over 2. All right. So in some books, they will rather check d prime over d. So either if you check d prime over d, then the limit is 0.185. But if you check d prime over x, which this is directly in the code, then your limit should be 0.37. And this must be checked. If you check and this is fulfilled, then we are saying that the compression still has yielded and the stress in the reinforcement will be this particular one. But if it is bigger than that, it means that the stress will be less than this, right? So in that case, you have to use this formula to calculate the stress in the steel in compression. Okay, this is strength of materials 1. Okay, ES is Young modulus of steel, and then strain in steel in compression. Okay, right. Now, so we are saying that if you calculate the d prime over x and is greater than 0.37, then you have to use equation, sorry, and it's less than, right? It's less than 0.37. You use this equation here to calculate the area of steel reinforcement for compression steel, and then the AS for area. No, this one, sorry. The previous formula is used to do the calculation. If your D prime, okay, if your D prime over X is greater than 0.37, then you have to use equation 11 and 12 to do the calculation for area of compression steel and area of tension steel instead of the previous one, okay? So you see that the change here is that in this formula you have FSC, FSC. And what do you do? How do you calculate FSC? The steel in the stress in steel, the stress in compression steel is simply Young modulus of steel than the strain in the compression steel. And Young modulus of steel reinforcement is a 200 times 10 to the power 3. Okay. So with this one, when you calculate, you have to use this equation here to calculate this parameter. 0.0035 over x minus d prime. And then the x in this formula, you calculate. So it's very simple. If this criteria, you get anything like this, then you calculate your x, calculate the epsilon SC, and then calculate this one, which you now use to substitute into this formula for the subsequent calculation. Okay? All right. So, in summary, in the design, in calculating the effective depth for single layer of reinforcement, as we have learned in the earlier design for singly reinforced, is the H minus the cover minus diameter of link minus diameter, half diameter of tension steel. Is that okay? And then as for the K, is the same thing, M over BD square FCU. And well, if you want to calculate the concrete capacity, ultimate capacity of a section, you can use this formula. And in this case, remember that the K is greater than the K prime. So in this case, what I stress on, the K in this formula is the K prime, not K, is K prime. And we know K prime is 0.156. Is that okay? Then the depth to the neutral as is D prime. And depth to the compression steel, as we have learned, okay, in the previous slide. So we have the compression, this is the section, and this is the link. This is the link. And you have your compression steel. And I said this centroid of compression steel to the compression face of the section is the D prime, which is called depth to compression steel. So it's simply the cover plus diameter of link plus half diameter of compression steel. Is that okay? Then As you remember, you need to calculate these two important parameters. You need to calculate the x and then calculate the d prime over x in order to ensure your section is under reinforced. And subsequently, we have this one. So if you check and your factor, if your d prime over x is less or equal to 0.37, you use these two equations to calculate area of compression steel, area of tension steel. And if your d prime over x is greater than 0.37, you will use these two equations. And remember that the FSC, you calculate x first, calculate epsilon c, do the substitution, and then you'll be able to calculate for this one. So the stress in the compression steel is here, is that okay? Which you have to use in a calculation. And then finally, you need to check your maximum steel area and the minimum steel area, and also the spacing of the bars, particularly for detailing purposes. Okay, so this table here seems to give summary of the formulas that will be required in the calculation or design of doubly reinforced sections. Is that okay? So you can take a snapshot of this particular screen, since we'll be using it to do our design, right? So take snapshot of this one too. And then finally, a snapshot of the screen. Good, so we'll be referring to this. And as I've indicated, last week lecture, we were able to identify where you can find these formulas in the code. And as I mentioned, the code is the Bible for the design. And so you cannot put the code somewhere once you do design. It is not, these formulas are not meant to be tuned into or commit to memory. You have to use the code, right? If along the line, you're able to commit some of these formulas to memory, that's fine, but I don't think it's a requirement. Okay. So in summary, the steps to design doubly reinforced sections. You calculate the design load, calculate design moment, effective depth, calculate the K, the lever arm, you calculate your D prime over X, right? Then you calculate the area of the reinforcing steel, and then calculate the area of the tension steel, and that of the compression. Check for maximum steel area required, and then you provide a sketch. So it's always important that in your design, you have to provide summary of the design in a sketch form so that it becomes very easy to use that information for detailing and for other purposes. All right. So on this note, you remember this particular table. Well, for those who don't know how to read, we will come back to this table. This is where you get your you convert the area of your steel into various diameters that can actually be used for detailing and construction purposes. Okay. So we'll do some work examples. And the first one we have here is the section shown below is to resist an ultimate design moment of 285 kilonewton meter. So the characteristic material strength are Fy 460 Newton per mm square and SCU 30 Newton per mm square. So you have to determine the area of reinforcement required. Is that okay? So now we have been given a cover of 30 mm, and we have been given the cross section also. So you remember, if, as we learned in the lecture 3, if the cross section has not been given, you have to decide on what we call the preliminary sizing, and you will be able to get the width and the depth, or the overall depth of the section. Is that right? Good. Now, as usual, as we get a question like this, the ideal thing is to convert or extract the necessary information from the question and put it down in this manner. So in this example, we are going to assume 25 mm diameter tension steel and 10 mm diameter links. You need this assumption so that you'll be able to calculate for your effective depth. Is that right? Now, step 1, you calculate your design load. Well, you see that this problem, we have been given the design moment. So we don't even need to calculate any design load again. Then we move to step 2, calculate the design bending moment. Again, the design moment had been given, so we will just state it here, 285 kilonewton meter. And I always want to tell you, remember to convert the kilonewton meter to Newton millimeter. Okay, this value should be 285, right? Not 185. Good. So from here, our next step is calculation of the effective depth. Okay, our next step is calculation of the effective depth. So as you remember, so this being our link, we have a steel here. Okay, this is the compression, and this is the tension zone. So this is the link, and we say we are using 10 diameter, isn't it? And then this and that are the main bars, and we are saying we are using T25. Okay, so the effective depth is from the top of the compression to the centroid of these bars, to the centroid, okay, to the centroid. So this one is essentially the D. And as you know already, the overall thing is the H, okay? So from the link to the exterior face here is the cover, is that right? So the cover, as you see, the H minus the cover minus the diameter of link minus half diameter of tension steel will give us our effective depth. And so 500 minus 30 minus 10 minus half 25 will give us 447.5. And this will be the effective depth. It's very important to calculate your effective depth well. Okay? So what I will tell you is that in calculating the effective depth, usually you would have to assume a diameter of your main bar so that you'll be able to use it for that calculation. So typically after the calculation, you may want to cross-check again whether your effective depth you use is fine. So after calculating effective depth, what next? Calculate the K. That's the 4. Calculate the K. So the K is what? M over BD square LCU. So this is the moment, right? Converted to Newton millimeter. And the B is 250. This is the D. Remember the D is squared, right? And then the FCU. And this will give us 0.19. And clearly you see that this value is bigger than K prime, which is 0.156. So because it's bigger than K prime, we say compression steel is required. This statement is very important. You must write it, or you may also write it as design section as doubly reinforced. Any of these, they are all is the same English, but you must make a statement. Okay? You must make a statement. Good, let's proceed. So step 5, you calculate the Z. Calculate the Z. And as I indicated earlier, in this W for we use the K prime, okay, which is 0.156. All right. Now, in calculating the Z, the code limits the Z to 0.95 D. So what I always entreat is that, first of all, you calculate what is inside this bracket. And you need to ensure your calculator work is good enough. So if you can't put all together on your calculator, you do it bit by bit. Don't substitute the value of the D, okay? So in doing this calculation, you get 0.777D. Is that okay? Comparing that to 0.95, we know it's less than what? 0.95D. So once it's less, we will adopt what we have calculated as the Z. We substitute the value for the D, and that gives us 347.71. It is important to note, in calculation of the Z, the code has limited the lever arm to 0.95. So let's say when you calculated this section, let's say you had 0.98D. Clearly, this one is bigger than the limit. So anytime it's bigger than the limit, you will adopt the limit 0.95D. Okay? You now adopt the limit as your Z. And that's typical decision we make during exam. So this one gives us the lever arm. Good. So step 6, you calculate D prime over X. But in first calculating the D prime over X, as I indicated, you have to assume again, we don't have the compression steel. So reasonably, we assume, okay? We don't have the compression steel. And it's from here to here, which is the D prime, okay? Now, in terms of assuming the diameter, typically because the reinforcement in the tension zone would usually be more than that in the compression zone, we sometimes assume smaller diameter for the compression zone compared to the tension zone. But if you assume 25 for tension zone, you can still use the same 25 for the compression zone. There will be no problem. Okay? Your assumption should be reasonable. Right. So the depth to compression steel is cover plus diameter of link plus half diameter of compression steel. And that will give us diameter of compression steel assume is 20. Okay? And that will give us 52.5. So the next thing you have to determine the depth to neutral as the X. And the formula is D minus Z over 0.45. This D was calculated, and the Z was also calculated in our previous step 5. We divide by 0.45, and we would have 221.76 millimeters. So after I've got these two calculations, I now substitute into the D prime over X. Is that right? I now substitute into the D prime over X. And now substitute into the D prime over X. So the D prime is this one, and the X calculated here. So as you can see, our answer is 0.237. And this is less than the 0.37 limit that was given. Is that right? So clearly, this is telling us that the compression steel has yielded. To that effect, the yield stress in the reinforcement in compression will be 0.95 Fy. So now that you have got this criteria clearly, that is less than 0.37, then you use this equation. So the step 7, you calculate area of compression steel, which is the AS prime. And that one is K minus K prime, FCUBD squared over 0.95 Fy D minus D prime. So you see we calculated the K. K prime is 0.156. FCU is 30. The breadth of our section, 250. The depth, effective depth, is 447.5. Remember, it's squared. And 0.95 is a factor for the reinforcement steel. And the yield characteristic strength of the steel. And then you have the D, effective depth minus the D prime. In doing this substitution and doing the evaluation, you get 296 millimeters squared. And when you do this, when you get here, the next thing is check for minimum steel area. And from table 3.25 and dealing with compression steel, the minimum steel area is 0.2% BH, right? The B is 250, the H is 500, and that will give us 250. Okay? So it's less than the AS prime. So now we will adopt the AS prime required. We will adopt this value now as the AS prime required. And that will be 296. Okay? 296 mm squared. So let me take you to the table, okay, where we get the reinforcement. And then, so 296, isn't it? The AS prime required, AS prime required is equal to 296 mm squared. Now, so you have to make a decision on your diameter. So let's say if I want to use 12 mm, then I have to check from this particular 12 mm line, what is the steel area, either equal or bigger, okay? That will be what? 339, okay? So look at the top. What do you see at the top? 3, which means 3T12. Is that okay? Then you write the AS prime provided is the actual area here, which is 339 mm squared. Well, maybe somebody also say that, okay, I want to use diameter 16. So diameter 16, 201 is less. You can use 603 is too far away from there. Okay, so use the 402. And if you look at the top, it means 2. We need 2T16. Okay, AS prime provided is equal to what? 402 mm squared. Okay, right. You should understand that design is both an art and science. So you have to be creative, you have to be artistic. Whatever that you are selecting, you should include engineering judgment, whether the thing can be fixed on the site, whether when we cast the concrete will be good enough, whether the spacing is fine. You have to look at all these things and decide on a number of bars. So if the number of bars is too many and is not giving you the chance, you have to change the bar size or adopt paired or bundle bars. Okay, good. So I'm going back to where we were. Okay, so this is where we were. So we had provide 2T16. AS provided is 402 mm squared. Good. So after this, step 8, you calculate the area of the tension steel. From the formula, K prime FC will be d squared all over 0.95 FYZ plus AS prime. Let us take very key note of this formula. In this formula, the AS prime here is the one you calculated, not the AS prime required. Because sometimes the AS prime required may not be what you calculated. So you have to remember that you have to use the area you calculated. Is that okay? If I say the area, when you did this calculation, the answer here is what I mean. That's the answer you are going to use. This answer, 296, is what you'll be using. Okay, so FCU, the 0.156 FCU 30, the breadth is 250, the D effective depth square 0.95 grade of steel, and then the Z, okay? Then you add the 296, which was the AS prime calculated in the previous slide. And adding 1542 plus 296, you get 1838 millimeters square. Again, check the minimum steel area. And because this is tension steel is 0.13% and is 1:3, far less than the AS. So we would adopt this one as our AS required, 1838. Okay, so once again, let's go there and make some interesting decisions. And then, so the AS required is 1838. So let's take note of that figure. I think I'll go to that table for the last 1838. Okay, so our AS required is equal to 1838 millimeter square. Okay, so let's say if I want to use 12 diameter, what would I need to choose? 12 diameter will even be more than 10 bars, which will not be good decision. So what about 16? If it is 16, 2010, okay, so I have 10 T16, okay, and the area is what, 2010. 20, AS provided is equal to 2010 millimeter squared. Okay. What if we want to use diameter 20? So diameter 20, the next one would be 1890, and to the top is 6. So we have 6T20. AS provided is 1890 mm squared. Well, let's take one more. Let's say diameter 25. We have 1960. So we have 4T25. What is it? 19 AS provided is equal to 1960 mm. So remember that the AS provided is the actual area from this table, which you can also do on your own. It's just multiplying the area of the bar by the number. That's all. Now let's look at something. Our section, right, is having a width of 250. Okay, it's having a width of 250. And we know that the minimum spacing should be aggregate size plus 5, which we looked at in the previous lecture. Okay. Now, supposing I'm adopting 10T16, look at this section. Oh, the depth is 500. So will I be able to arrange this 10T16 here? The concrete cannot even pass through. Okay? So if that is not possible, then it means you need to adopt either having the bars in layers, okay, or bundle bars. But let's see the T6, the diameter 20. So arranging all the 6 bars down here will not create enough space. So in a proper way, you could rather adopt to do a double layer like this. You get it? So if arranging all the bars in one layer will not create space for concrete to pass through and all that, then you have to change, either you use the double layer or paired or bundle bars. You get it? So if we say paired, if it is 2 bars paired, you have to tie this bar with binding wire before you place it there. If it is bundle, maybe all these 4 bars might be tied with rod before binding wire before you place it there. So you see, design is both science and an art. So you have to use your judgment to select the right steel, not because the total number of the diameter you are selecting is giving you the provided area or the required area. So that's it. Once you add everything and you get, no. Arrangement of the bar also becomes a very important decision that you must be made. And so in doing this selection, you look at all these stuff in brief and make sure in terms of site work, the whatever you are proposing can be dealt with on site without trouble. And after we have constructed the elements, we have exactly what we expected and assumed for our design. Is that okay? Good. So in this case, this particular problem, I adopted 60/20 and the AS provided is 1890 millimeter squared. And this 1890, the sketch details of the section. So essentially, it's important to check the maximum steel area, which is 4% of the concrete section. It's very important to ensure that your steel area is no more than the maximum. But that may result in excessive reinforcement, congestion, and can also lead you to enter into the zone of over-reinforced section. Is that right? Then the final step, which is the step 10, is that sketch the section. After all the calculation, it is very crucial to provide a sketch. So in providing the sketch, you see that you are able to indicate the compression steel you provided and then the tension steel, the proposed arrangement you have had. Is that okay? Now note that anytime you are providing a sketch, you need to remember to include the concrete cover because all these are important things that need to be required, that are required in doing detailing. Okay? You provide a sketch of the detail, but there must be proper detailing of the work which can be used for construction purposes. Is that okay? I think this is okay. You just 10 steps and you are through. Right? This should not be any big issue. Great. So this, as we have done, is a simple way of designing doubly reinforced section. So let's do one more example. Now, a simply supported rectangular beam of 9 meters span carries characteristic dead load 4 kilonewton per meter and imposed load of 5 kilonewton per meter. The beam has breadth of 225 and overall depth of 400 mm. The characteristic material strength are SCU 30 and FY 460, and concrete cover is 30. You have to calculate the area of steel reinforcement required. Okay, good. So what do? Well, we have a section, we have a couple of information. Extract all the information and put it down as the given information. This is the first and the fundamental step. You should be able to extract information from the question. And that everybody should be able to do so, isn't it? Good. So from this extracted information, now we have been given the loading diagram, right? So the first thing that we would have to do is to calculate our design load. And the formula is 1.4 GK plus 1.6 QK from table 2.1. Okay? So 1.4 GK, dead load is 4, and the imposed load is 5. And this will give us 13.6 kilonewton per meter. And I always encourage you, okay, after you have finished calculating the design load, draw the beam section and indicate the design load on it. It's very, very important to do this because you will now subject this one to analysis. Okay. So now you have been able to calculate your design load. What is the next step? You have to calculate your bending moment, and then in order to draw your bending moment diagram. Now you see that this particular beam here is a standard beam, right? It's a standard case. So if you know the formula for calculating maximum moment, apply the formula, draw the bending moment diagram, and off you go. If you don't remember the formula, or if there is no such formula available in books, then you have to calculate the reactions, cut sections, and calculate your various bending moment values. And after that, you draw the diagram. And from the diagram, the maximum moment from the diagram becomes your design moment. Okay? And because this one, the formula exists in books, maximum moment for a beam of this nature is omega L squared over 8. And this is 13.6 times the span squared over 8. And this will give us 137.7 kilonewton meter. All right. So remember, it's not negotiable. You must always draw the bending moment diagram. Don't say this is just a standard, no. As part of the design process, it's important to draw the bending moment diagram. If you are dealing with shear, you have to also draw the shear force diagram, right? So you can't say because it's a simple beam, the bending moment diagram is not important. No, it's very crucial to do that. So from this bending moment diagram, the maximum moment is 137.7 kilonewton meter. So that's a step 2, right? Then step 3, calculate the effective depth. Calculate the effective depth. So the effective depth, as we have learned again and again, is what? H minus cover minus diameter of link minus half diameter of tension steel. Again, tension steel is assumed to be diameter 25, right? And that will yield 347.5 mm as our effective depth. Once we are able to calculate effective depth, the next step, which is step 4, is to calculate the K. And the K is M over B D square FCU. And I keep reminding you, you must convert the kilonewton meter to Newton millimeter by multiplying by 10 power 6, right? Okay, so the B is a 225, which is the breadth of our section. The D is what is up here, which should be squared. Some students forget to square. And when you do this kind of gross mistakes, the structure may collapse because factors are not supposed to be taking care of mistakes. Okay, and then the 30. So we get 0.168. Again, if you compare this with 0.15, you see clearly this one is bigger than 0.156. So once this condition is met, we say compression steel is required. In other words, design the section as doubly reinforced. Doubly reinforced section. So then we move to step 5. You calculate your lever arm set. Again, remember that in this calculation, the lever arm, the K in this formula is K prime, not K. I keep stressing this because when you miss the formulas, whatever that you do thereafter amount to nothing, right? So try to evaluate what is in this bracket first, and evaluating that, you get 0.779 D. Okay. Then that's obviously less than 0.95 D. So we adopt our value and then substitute the D and do the calculation. Get 270.01 millimeters as the lever arm. Okay, so that is step 5. So after that, we have to determine our D. We need to calculate a D prime over X, which is very important to check whether the compression steel has yielded or not. And then you find the required stress level in the reinforcement. So the D prime, we are assuming diameter of what? 20. Cover plus diameter of link plus diameter of compression steel. And this will give us 52.5 mm, right? Then you calculate that to neutral axis, which is D minus Z over 0.45. So the effective depth, the lever arm we just calculated, and this will give 172.2 mm. Then you now calculate the factor D prime over X. So the D prime over X is giving us 0.31, which is obviously less than 0.37. So this tells you the compression steel would yield, and that matter, the level of stress in the steel will be 0.95 Fy. Okay? Now, then the step 7, now that we have been able to establish that, we can now select the appropriate formula for calculating the area of steel in compression and in tension. So, with the area of steel in compression, AS prime, K minus K prime, FCUBD squared, 0.95 Fy, D minus D prime. So this, we do the right substitution. This is the width, effective depth. 0.95 is factor, positive the grade of steel. If I give you grade 250 steel, don't come and put 460 here. No. You use the grade of steel. If the grade of steel is 500, use 500. Is that right? Good. Then the D minus D prime. Evaluating will get 76 millimeters squared. Then check the minimum steel. Okay. For compression steel, 0.2% BH. And that will give us 180, greater than AS prime. So if your minimum steel is greater than the area of compression steel, then adopt the minimum now as the area of compression steel required. The rule is that if your reinforcement in the concrete is less than the minimum, the code assumes that you are designing a non-reinforced member. So if your steel area is less than the minimum, it means though you may think you have provided steel in the concrete, but it's considered as a plain concrete member. So that is why it's important to ensure you always meet the minimum. So in this case, 180 is bigger than 76. So we would adopt the 180 as our AS prime required. And then from that same table, we are selecting T2, 2T12, and AS provided of 226 mm squared. Because I've shown you that table and we've done that extensively, I know you can do this on your own. So now we are done with the compression steel. We go and calculate for the tension. So with the tension steel, AS is K prime, FCUBD squared over 0.95 FYZ plus AS prime. You see the actual AS we calculated is what? 76 mm squared. So that is what we will use for this, not the AS prime required, right? So we do the substitutions. This is the grade of concrete, section width, effective depth, the factor, characteristic strength of reinforcement, and this is the Z, the lever arm, then plus the 70. So these together have 1154 mm squared. Again, check minimum steel. Of course, this is less than that. So we adopt what we have calculated as the required. Then from that same table, we select the steel diameters. We are selecting 40-20. That will give us 1260 mm squared. Let us understand that design is artistic and scientific. And so I'm not expecting that if 4 of us we are designing, we are all going to select the same diameter of steel, the same number. No. It's based on judgment. So individual judgment, engineering judgment, which must be a sound judgment with understanding, then you will select the right steel, which will now be used for detailing purposes. Okay? Great. Now, you check the maximum steel area, which is very crucial. Make sure your steel area doesn't exceed that. And then the final step, step 10, we will now provide a sketch. Okay, so as you can see here, compression steel and the tension steel have been arranged in this way. Okay, let us know that design is both science and an art. So I can combine a number of reinforcement sizes. I can decide to, let's say, choose 3T20 plus 2T16. Once it will give me the required area, that's enough. So there's no rule that all the reinforcement down here must be the same diameter. There's no such rule. Okay? You can have bigger and smaller size, but typically the bigger ones will be at the bottom while the smaller ones will be placed on top. And as usual, you have to indicate the cover of the concrete. So as you can see, this is very simple. And of course, all the structures we are living in, this has been the approach that has been used to do that design. Is that okay? Good. There's no link provided because we have not yet designed link. We've not designed any link, so we cannot just put any link around it. That's it. So with working two examples, the various steps will not change. And so you are expected that, or it's expected that when you have a similar case, you will be able to do design of the steel, of the doubly reinforced section, typical, right? And there's some practice question, which is this one. So I want to entreat all of you, ensure that you do the practice questions where you require to ask questions, ask the questions. Don't be a spectator, be a participant. And I keep saying, when we have an online lecture, you have to have your calculator, everything with. And the practice question that I've been given was for you to practice. Said that the more you practice, the more you may be facing certain challenges and you overcome them. And those challenges will no more become a challenge, it become your strength. And so don't just be reading and say, I can do it. Practice, because practice makes perfect. Is that it? All right. So essentially, this will bring us to the end of lecture 4. Now, before I exit, I want to let you know the coursework is ready, and the coursework, you are going to use a special sheet for calculation. You are not going to use the usual, whatever, no, okay? So this sheet is here. This column is called reference. This is calculations. And this side is the output, okay? So the coursework, I'll give you this particular sheet. You have to make print or make copies of it and use it for the coursework. So for example, what is the reference? Let's say you are picking something from the code. If it is table 3.25, you write it in this column. And then the middle here is for all calculations, including all your diagrams you are going to draw, okay? All your bending moment diagrams, shear force diagram, everything, you do it in the middle here. And then the output. So some of the output could be the reinforcement areas you have had, the effective depth, important information that you will be needing often. So that if you are looking for it, you don't go through the calculation, you just go to the output and look for those information there. Is that right? So if it is clause 3.4.4.4, you write it. So all the references, the code references will be written in this column, and then the calculation in the second column, and then important information that you may use again and again, or you refer to often, you provide this information under the output. And so this will also be provided for the purpose of your coursework. So in summary, today we have learned how to design doubly reinforced sections. And we have also learned that when the design moment is greater than the moment capacity of the section, you need to additional strength, because the concrete alone cannot do the work. So you provide steel reinforcement in the compression zone. So in the compression zone, you have the steel plus the concrete doing the work. But the tension zone, the steel only. As I said, the concrete under the tension zone will crack. Once the concrete has cracked, there's no more effective strength in it. So usually the concrete in tension zone for reinforced concrete design is ignored. Okay? The tension zone concrete is ignored. And we have learned this. We have gone through few of the formulas, and all these formulas for the doubly reinforced, you can find them in clause 3.4.4.4 of the BS 8110 part 1. And this is the same code you'll be using for exam. I don't see why you would want to have everything from your head, because expert engineers, expert structural engineers, everybody is using the code. And so I don't know why you, a beginner, will say, I have everything in my head. That cannot be true, right? So your duty is to learn. We don't refer to code by pages, by the clauses we do, not pages. So you will not hear me talking about page so and so. Is the clause, which I have also shown you how to use the code, how to read the clauses, and how to look for whatever you want in the code. Is that okay? All right. So looking at what has been just done, design is so sweet like biscuit fried rice. And so it's very interesting. Commit yourself to learning and you become a master of it. Okay? So thank you very much for participating in today's class. If you have any questions, you can reach out to me and I'll be of good help to you. You may also leave comment section in the YouTube channel, wherever you find this video. And then if it becomes important to send me WhatsApp messages, you can do that and I'll be able to clarify. But please take your time and go through this, listen again and again, and continue to do until you become perfect. Okay. So on this note, I'll say thank you for joining today's class. And it's been a wonderful time with you. I hope that you have learned something. I hope that you have understood what we have done. Otherwise, you have the luxury of, again, continue to go through again and again until you get whatever that may be confusing you. So thank you very much and have a blessed time. Bye-bye.